Okay, so let's quickly go through quiz 2. For the first problem, find f prime of x using the limit definition of the derivative. Okay, so what we want to do here, we're given the limit definition. I think that a helpful thing, at least for me, when I'm going through these problems, is to say, all right, if f of x is 3x squared, then f of x plus h is 3 times the quantity x plus h squared. And I'm going to go ahead and simplify this before I bring it back over here to this limit definition, right? So I have 3 times x squared plus 2xh plus h squared, and then I distribute the 3 to get 3x squared plus 6xh plus 3h squared. Okay, so that's what we're going to plug in for this f of x plus h. We have 3x squared that we plug in for f of x. Okay, so our f prime is going to be the limit as h goes to 0 of 3x squared plus, that should be 6xh plus 3h squared, and then minus f of x, so minus 3x squared. If there were more terms in the f of x, I would want to make sure I put them all in parentheses so that the negative gets distributed to all of the parts. Okay, so now the 3x squared minus 3x squared add to 0. So I'm going to have the limit as h goes to 0 of 6xh plus 3h squared all over h. And now everything in the numerator has an h in it, so I can factor that h out. So we have h times 6x plus 3h, and we have an h in the denominator. So the h's that are factored out will cancel. So this is the limit as h goes to 0 of 6x plus 3h. And now we solve the limit by doing direct substitution. So I don't write limit anymore because we have evaluated it. So we get 6x plus 0, or just 6x. So f prime of x is 6x. All right, any questions on that one? Okay, let's go on to number 2. Find the derivative of this big and terrible product. Okay, we don't actually have to use the product rule here if you were to multiply all of this stuff out. But since we're not going to simplify our answer, then multiplying all this stuff out is just a lot of extra work that we don't really need to do. So we're just going to do the product rule here and say, okay, I have the derivative of this first piece, x cubed minus 4x plus 2, times the second piece left alone, plus the first piece left alone, times the derivative of the second piece. Okay, so the derivative of 3x to the fourth plus 5x squared. Okay, the derivative of x cubed minus 4x plus 2 is 3x squared minus 4, and then plus 0. Okay, so then I just copy down this other stuff. And the derivative of 3x to the fourth, oops, I left something off here at the end, minus 7. Okay, the derivative of 3x to the fourth plus 5x squared minus 7 is 12x cubed plus 10x, and then plus 0. And since we don't have to simplify, this is it. That's all we have to do for that one. Just the product rule. Right, so let's go on to number 3. This one is just a quotient rule, and I don't think there's a way to really get away from that. Okay, so let's go ahead and set up the quotient rule. So we have the derivative of the top times the bottom left alone minus the top left alone times the derivative of the bottom all over that bottom, that denominator, squared. Okay, so let's evaluate these derivatives. The derivative of x squared minus 3x is 2x minus 3. I'm going to make sure that that's in parentheses, otherwise it would just look like negative 3 times this other stuff. And the derivative of 9 minus 2x is, 9 minus x squared is 0 minus 2x, or just negative 2x. And once again, because the problem says don't simplify, we'll just leave it like that. That's fine, right? So we're just applying the quotient rule, nothing fancy. Any questions over the quiz? Okay, I think that one generally went pretty well. So now let's go to homework and review questions. Maybe we'll do homework first.
I had a question on 3.7, number 5 and 16.
Okay. Okay, so here's 3.7, number 5. Before I answer this question, just for the benefit of everybody, what I want to do is pull up the book. I just want to look at something from 3.7 that I think will make this a little bit easier to follow. Okay, so in 3.7, they look at derivatives of inverse functions. Now, the way that I presented the material on Blackboard, I didn't put 3.7, 3.8, 3.9. I put 3.7 later because the stuff that we do in 3.7 you can do using implicit differentiation. I think it's a little bit less confusing, but it's just kind of another way to attack it, right? So the idea is that by taking advantage of this symmetry that you have between a function and its inverse, you can figure out slopes of tangent lines, okay? And so we get this little inverse function theorem that if I have a function and I have its inverse, then the derivative of the inverse function is 1 over the composition, right? Of I plug the inverse into f prime. Okay. So this is what we want to use, I think, for these problems, right? So let me see if I can write this on the screen so that it'll stick when we go ahead and switch over to the homework. Okay. So if g of x equals the inverse of f of x, then the derivative of that inverse function, the derivative of g, is 1 over f prime of g of x. All right. Now, let's go ahead and flip back to the homework question. For the function y equals f of x equals 8 over 1 plus x squared, find the slope of the tangent line to its inverse function at the point 4, 1. Okay, so I want the slope of the tangent line to the inverse. So what I want to find, you know, if I write g of x is the inverse function, if g of x is the inverse of f, then what we're doing is we're saying find the slope of the tangent line to the inverse. So g prime at the point 4, 1. So I'm plugging 4 in for x and 1 in for y. Okay, so we'll come back to that. Okay. So using my formula, this is 1 over f prime of g of 4, and g of 4 is 1. So it says 1 over f prime of 1. So what I'm going to do is I'm going to compute the derivative here and then plug 1 into it. Okay, so f prime of x, there's, I guess, two different ways that we could go about doing this. You could write this as a quotient, which is fine. If I rewrite this as 8 times 1 plus x squared to the negative 1, I could also do this derivative using the chain rule. Okay, I'm just going to set this up as a quotient rule because I think that's how most people probably would have started this, but I think it's less work as a chain rule. Okay, so if I do this as a quotient rule, we have the derivative of the top times the bottom left alone minus top times the derivative of the bottom over the bottom. Oops. Okay, over that bottom piece squared. The derivative of 8 is 0, so I just get 0 minus 8 times, and the derivative of 1 plus x squared is 2x. Okay, so f prime of 1 is negative 16 times 1 over 1 plus 1 squared. 2 squared is 4. So I get negative 4 as the slope of the tangent line. So they have negative 1/4. Did I mess that up? Okay. Here's the mistake that I made back here. Let's go ahead and point this out. And this is, I think, an easy mistake to make, and this might have been where you ran into trouble. It says find the slope of the line tangent to its inverse function at the point 4, 1. So if I plug in to my function and I plug 4 in, I get 8/17, not 1. If I plug 1 into the function, I get 4. So what that lets me know is that this point is a point on the inverse, which I think is what we plugged in. Oh, I'm sorry. Everything is fine. I did not make that. Okay, sorry. Anyway, this is a possible point of confusion because you want to be careful of where this point is. And this is a point on the inverse. Okay. And that, all right. So when I found f prime of 1 equals negative 4, remember that back here, g prime of 4 is 1 over f prime of 1. So 1 over negative 4. So that's my slope of the tangent line. And then to find the equation of the tangent line, I have a slope and we have a point. So we can just write the equation. So y minus 1 equals the slope times x minus 4. So minus and negative is plus. 4 times a fourth is 1. Add 1 to both sides, and I get negative 1/4 x plus 2. Okay, does that make some sense?
Yes, thank you.
Okay. Since this is also a review day, what I want to point out is that on the review sheet, there were no questions where I asked you to find a slope of the inverse of a function. So while this is, I think, something that is helpful to go through, at the same time, because there's a limited amount of stuff that we can really test over in a reasonable amount of time, this got cut from the test. So you can notice that it's missing off of the review. So that means that you won't actually be tested on this. So this formula that we had over here, that's not something that you should bother memorizing or anything like that. It's something that you can just look up, note. It's interesting, it's useful, but it's not something that we're going to memorize and use going forward. Okay, another homework question?
Could you also do 16 from 3.7?
Oh yeah, I think you asked for that, so I'm sorry. Okay, so here's 16. A television camera at ground level is 2,000 feet away from the launching pad of a space rocket that is set to take off vertically. Right? We have a little diagram here. The angle of elevation of the camera can be found, and it gives you theta equals tangent inverse of x over 2,000, right? Which we could find, right? Because I could see, all right, there's theta. Tangent of theta is opposite over adjacent, so x over 2,000. If I solve for theta, I use the inverse tangent. Okay, so x is the height of the rocket. Find the rate of change of the angle of elevation after launch when the camera and the rocket are 3,385 feet apart. So rate of change of the angle of elevation. So what I want to do is find the derivative of theta. Oops, I wrote. Yeah. Oh, hold on, let me back that up. Okay. Find the rate of change of the elevation. So the derivative of theta with respect to x. Okay. When the rocket and the camera are 3,385 feet apart. So if I label the distance between the rocket and the camera as, say, distance d, find this when d is 3,385. Okay, so what I'm going to do is I'm going to start with this equation that we were given. Theta is tangent inverse of x over 2,000, right? Or you could think of it as 1 over 2,000 times x. Okay. And so what we want to do is take the derivative of both sides. Now, once again, I'm going to refer back to the book really quickly and just point out some things that we get. Oops. That real quick. They show these in 3.7. Okay, back in 3.7, we had derivatives of the inverse trig functions. And so here's sort of a list of all of them. And in particular, I want to look at the one for tangent inverse. So the derivative of tangent inverse of x is 1 over 1 plus x squared. And I don't know if they redo. No, they don't redo these. Okay, so what I'm going to do is I'm going to use that derivative formula. Okay, so let's just write down that derivative formula really quickly. So the derivative of tangent inverse of x is 1 over 1 plus x squared. Okay, what I want to do is I want to find the derivative of tangent inverse of a function of x. So I'm going to use that derivative formula, but I have to use the chain rule because I have an inside function. So when we take the derivative of theta, right, on the right-hand side, the chain rule says, okay, I have tangent inverse of a function. Use your derivative formula like normal, but don't plug in x. Plug in the inside function. So I'm going to get 1 over 1 plus 1 over 2,000x, which is then squared, and then times the derivative of that inside function. Okay, and the derivative of 1 over 2,000 times x is just 1 over 2,000. Okay, now what I want to do, this is a formula for the derivative of theta. What I want to do is I want to find that at the moment when d is equal to 3,385. What I need to do is figure out, all right, when that distance is 3,385, what is x? Because x is what I need to plug into my derivative. Okay, so I'm going to go back to here and I'm going to say, all right, using this diagram, if I know a value for d, can I find a value for x? Okay, and one easy way to do that, I think, is just to say, all right, this is a right angle, so I could use the Pythagorean theorem. We could also use a trig function, and that would work. Okay, but since I don't know the angle theta, I think that using a trig function is going to be more complicated. So I'm just going to use the Pythagorean theorem and say, okay, 2,000 squared plus x squared equals d squared, but in this case I have a number for d, 3,385. Okay, so let's go ahead and square those out. So 2,000 squared is 4 million plus x squared equals, then I take 3,385 and square it, and I get 1,145,822.5, right? So a little over 11 million. Okay, so we subtract 4 million from both sides. So x squared is equal to 7,458,225, and then we're going to go ahead and take the square root of that. Normally when I solve using a square root, we would write plus and minus, but this is a distance, so I only want the positive one. So we're going to get 2,730.975. Okay, and so what I'm going to do is I'm going to plug that into the derivative. So d theta dx when x is 2730.975 is 1 over 1 plus 2730.975 over 2,000 squared times 1 over 2,000. And I end up with 1.74547. Okay, and my angles are in radians and my distances were in feet, so radians per feet, and they sort of give me that. Oh, I'm sorry. I wasn't looking carefully enough. My calculator gave my answer in scientific notation. It says 1.74547, and then my calculator gives this little e negative 4. That's the calculator shorthand for scientific notation times 10 to the negative 4th. So I have to move the decimal place 4 places to the left. So 1, 2, 3, 4. So 174547. All right, does that one make sense?
Yes, thank you.
Okay, it's definitely a little on the complicated side. Okay, any other homework questions?
Could you go through question 6 from 3.7?
Okay, let f of x equal, and then we have in parentheses 8 sine x plus 5 cosine x times tangent inverse of x, then find f prime of x. Okay. So what I'm going to do here is I'm just going to take a regular derivative, and I'm going to make use of that formula that we just had a minute ago. The derivative of tangent inverse of x is 1 over 1 plus x squared. Okay, so then if I want to take the derivative of this thing, I'm doing a product rule. Okay, so f prime of x is going to be the derivative of the first one. The derivative of 8 sine x is 8 cosine x. The derivative of 5 cosine x is 5 times negative sine x times tangent inverse x left alone, plus this first piece left alone, 8 sine x plus 5 cosine x, times the derivative of tangent inverse x, which is 1 over 1 plus x squared. Okay. And that's basically it, right? There's not really any meaningful simplifying I can do here. You can maybe rewrite it. You could write a minus 5 instead of 5 times a negative, but that's it.
Okay, thank you.
Okay. All right. Any other homework questions?
Yes. 3.7 question 4. Also, I kind of want to ask, so this like inverse, I guess, chapter won't be on the test?
Well, this is one of the things where it's it's a little more challenging because of the both summer and blended, everything moves very fast. What I would have liked to do is show you how we can arrive at the same spot, either using this inverse function theorem or using implicit differentiation, and they both sort of get us to the same spot. What I think that I'd prefer to do is just sort of double down on just implicit differentiation, and then let this one pass by. So the short answer to your question is yes, this is not going to be on the test.
Okay, thank you.
Okay, for the function y equals f of x equals x cubed minus 2, find the derivative of f at x equals negative 1. So the first thing we're going to do is just take a regular derivative of this function. Okay, so f prime of x is 3x squared and then minus 0. So that's it. So f prime of 1 is 3 times 1 squared, which just gives me 3. Okay, next find a formula for x equals f inverse of y. So what we're going to do is we're going to take this function and we want to find its inverse. Okay, so if I have y equals x cubed minus 2, what we can do is we can now solve for x, right? So add 2 to both sides, and then cube root both sides. Okay, so I solved for x, so I now get a formula for the inverse. So f inverse of y is the cube root of y plus 2. Or I can write that as y plus 2 to the 1/3 power. Okay, now finally find the derivative formula, the derivative of f inverse of y at y equals f of negative 1. Okay, so there's, I think, idea here is two different ways of looking at this. If I look at the hold up real quick. If I look at the inverse function theorem, okay, then the derivative of the inverse is 1 over f prime with the inverse plugged in. Okay, so one way to do this using the theorem, okay, and then you know the other way would be just to, you know, since I have formulas for it, just to compute derivatives, okay. Okay, so without the theorem, to find the derivative of f inverse of y, I'm just going to treat y as my variable and I differentiate this, right? So this is y plus 2 to the 1/3 power. So the derivative of f inverse with respect to y is just 1/3 y plus 2 to the negative 2/3 times the derivative of the inside stuff. And here y is my variable, so the derivative of y is 1. Okay, so that's taking the derivative of f inverse, and then it's saying at y equals f of negative 1. Okay, if I plug negative 1 in for x, f of negative 1 is negative 1 cubed minus 2. Negative 1 cubed is negative 1, and minus 2 gives me a negative 3. Okay, so we have x equals negative 1 and y equals negative 3. For the inverse function, I want to plug in a y value. That's why they have f of negative 1. That gives me the y value, negative 3. So the derivative of f inverse with respect to y, when I plug in y is negative 3, is 1/3 negative 3 plus 2 to the negative 2/3. Okay, so I get negative 1 to the negative 2/3. Okay, it's probably easier to see how to plug this in if I write this as 1 over negative 1 to the 2/3 power. So if I square first, I'll have a positive 1. I cube root it, I get 1, and so we just get 1/3 here. Okay. Using that theorem, okay, the theorem says that if I take the derivative and I want to plug in a value, I just take 1 over f prime with that thing plugged in. Okay, so just doing this whole thing a different way, the derivative of f inverse with respect to y, when y is f of negative 1, is 1 over f prime of, show this again. I take 1 over f prime with my inverse function plugged in. Okay. All right. Okay, so f prime of x is 3x squared. Okay. And I've already figured out like my x's and y's, right? So if I plug in my negative 3 for y, then I get negative 1 for x. So this is just 1 over f prime of negative 1, which is 1 over 3 times negative 1 squared, which is 1/3, right? So you can see, you know, same. Okay. Another homework question?
Could we go to section 3.9, question 10 and 12, please?
Yeah. Okay, so 3.9, question 10. F of y is y to the 4th over 4 times ln of y minus y to the 4th over 16. Find f prime of y. Okay, so here there's no x's, it's all just y, so they're just changing the name of the variable on us. So we don't have to do anything special with that. Okay. What I am going to do, though, is when I go to differentiate this, in this first term, I have a product. Okay, and then I have this second thing by itself. Okay, so if I start off with writing f of y is, I'm going to write this as 1/4 y to the 4th, and think of that as one piece, times ln of y as my second piece. Okay, and then this 1/16 y to the 4th, I'm going to think of as its own separate thing. But if I think of, dividing by 4 is the same as multiplying by 1/4, I don't really need to think about this as a product. This is just a constant, right? So, a constant 1/4, I don't need a quotient rule or anything like that for. All right, now when I go to take the derivative, we're going to have the derivative of 1/4 y to the 4th. So the 1/4 is a constant multiple, it hangs out. When I differentiate y to the 4th, I get 4y cubed, okay, times the ln of y on its own, plus the 1/4 y to the 4th on its own, times the derivative of ln of y, which is 1 over y. So in this problem, y is my variable, so I'm not doing implicit differentiation here. I'm just, treating y as the regular variable. It's derivative natural log of y, 1 over y. Okay, over here, when I differentiate, I'm going to think of this as a negative 1/16. The derivative of y to the 4th is 4y cubed. Okay, so now let's simplify a little bit. 1/4 times 4 cancels, so I get y cubed times ln of y. And then I have plus 1/4. Y to the 4th times 1 over y is y cubed. Okay, and then minus 1/16 times 4 is 1/4 y cubed. So positive 1/4 y cubed minus 1/4 y cubed add to 0. So I get y cubed times ln of y. Okay, does that make sense?
Yes, thank you.
Okay. Another homework question?
Could you do question 12?
Oh, yes, you did ask for that. Thanks. Here we go. All right. Here, y is 3 plus 2 times x to the power of x. We want to find the derivative. And they tell us that we need to use logarithmic differentiation, but that is the only way to go about this. Because what I have in my function here is a variable base and a variable exponent. So it's not a power function and it's not an exponential, so we cannot differentiate this as it is. So I'm going to go ahead and oops. Try that again. I'm going to go ahead and write this out. And then I'm going to take the natural log of both sides. And I'm going to use my properties of logs to break this up. So in this case, I have log of stuff to a power. I can bring that power down out front. So I have x times ln of 3 plus 2x. Okay. And now what we can do is take the derivative of both sides. When I differentiate natural log of y, I get 1 over y times the derivative of my inside function. The derivative of y is dy dx. Because I want to find the derivative with respect to x. X is my variable, not y. So here I'm doing implicit differentiation. On the right-hand side, I have a product. So I'm going to use the product rule. The derivative of x is 1 times the second piece left alone plus the x left alone times the derivative of the second piece. When I differentiate this, I get 1 over the inside function times the derivative of the inside function. Okay, the derivative of 3 plus 2x is just 2. Okay, so now I've differentiated. Now I'm going to multiply both sides by y. So on the left, these cancel, so I just get dy over dx. On the right, I get y times the stuff, ln of 3 plus 2x plus 2x over 3 plus 2x. And then for my last step, I'm going to replace y with its formula. And I was given that y is 3 plus 2x to the x. So I have 3 plus 2x to the x times ln of 3 plus 2x plus 2x over 3 plus 2x. And just be careful to mind your parentheses.
Okay, got it. Thank you.
Sure. All right. Any other homework questions? Okay, if there's nothing more on the homework, then we can switch over and look at the review problems. I posted answers to these, so I don't know that I need to go through every single problem, but I can certainly go through as many as you would like to see. So, how many do we have on that? 13. Okay, so are there any problems off the review that you would like to see me go through in detail?
Can you do number 2, please?
Yeah. All right, so here's f of x over x squared plus 4. Find f prime using the limit definition of the derivative. So I know that the limit definition of the derivative, f prime of x, is the limit as h goes to 0 of f of x plus h minus f of x all over h. And what I like to do, just like I said in the quiz, is I like to write out, okay, here's f of x, and then I like to write out f of x plus h. So I replace my x's with an x plus h. And I like to simplify this as much as possible. So this x plus h squared, I'm going to go ahead and FOIL that out. So I get x squared plus 2xh plus h squared. Okay, and there's not really more simplifying that I can do here, but at least I have f of x plus h fully written out. So now I can plug it in into my limit definition of the derivative. So f of x plus h is this big terrible fraction, x plus h over x squared plus 2xh plus h squared plus 4. And then minus f of x. F of x is x over x squared plus 4. And this whole thing is divided by h. Okay, so there's a lot of work to do here. We're going to take this, one step at a time. I have two fractions that I want to combine together, so I need a common denominator. They don't have anything in common. I know it looks like the x squared and the 4 are nice common pieces, but when we're looking at common denominators, we're looking at common factors, and this is all one big factor. This is all one big factor, so they don't have any factors in common. So the fraction on the left, I have to multiply by x squared plus 4 on top and bottom. Fraction on the right, I have to multiply by x squared plus 2xh plus h squared plus 4 on top and bottom. Okay, now there's two other things I'm going to do in this next step. In order to avoid losing a negative, I don't like to subtract fractions, so I'm going to add a negative fraction. I'm going to make that negative just be right on the x, and that way I don't have to worry about losing the negative. The other thing I'm going to do is dividing by h. I can think of h as being an h over 1, and instead of dividing by it, I'm going to multiply by the reciprocal. That just means that I don't have to write multiple layers of fraction. I'm just going to have one layer of fraction throughout. Okay. So I'm not going to do any multiplying out yet. I just want to write out what I have so that I don't get confused. So we have x plus h times x squared plus 4, okay, over our common denominator. And since we got a common denominator with this other one, we can combine those together. So I have minus x times x squared plus 2xh plus h squared plus 4, right? It's over the same denominator, so we can just subtract them over that common denominator. And then instead of dividing by h over 1, I multiply by 1 over h. Okay, so at this point, I've turned my calculus problem into a lot of algebra. I just need to be very careful about multiplying things out. I don't want to touch the denominator, though. There's no reason to do anything in the denominator. It's not wrong if I do, but it's not helpful, and I want to limit the amount of work that I do. Okay, so in the numerator, multiplying out this first thing, x times x gives me x squared, x times 4 is plus 4x, h times x squared is, and I'm going to just use the convention of always writing the x's first, so an x squared h. And then h times 4 is plus 4h. Okay. Over here, I just have a negative x to distribute to all 4 of these terms. So minus x cubed minus 2x squared h minus xh squared minus 4x. Okay. The denominator we leave alone. And, multiplying by 1 over h is just throwing that h in the denominator. Okay, now let's look for things that add to 0. So I have a mistake because x times x squared is x cubed, and I wrote x squared. Okay, it's easy to do, I guess. All right, now I look for things that add to 0. So x cubed minus x cubed add to 0. Positive 4x minus 4x add to 0. I think that's basically it for things that add to 0, but I can combine one more thing. X squared h and negative 2x squared h. I have 1 of something minus 2 of something. That gives me negative 1 of that thing. Okay, so x squared h minus 2x squared h will give me a negative x squared h. And then I have plus 4h, okay, and then minus xh squared. Leaving the denominator completely alone again. All right, now the numerator, everything left has an h in it. If that's not the case, that means you made an algebra mistake somewhere. Okay, but everything left has an h in it, so let's factor that h out. So if I factor out the h, I get a negative x squared plus 4 minus xh. And the denominator, again, we're just leaving alone. It's along for the ride. Okay, now I can cancel this h that I've factored out of the numerator with the h that is still factored out of the denominator. That's sort of our key piece here. Now that I've canceled this h in the denominator, I can use direct substitution. Okay, so I get negative x squared plus 4 minus 0 over x squared plus 0 plus 0 plus 4 times x squared plus 4. Okay, so I can write this as negative x squared plus 4 in the numerator. I have x squared plus 4 times another x squared plus 4. That's x squared plus 4 squared. Okay, so that's finding this derivative using the limit definition, which is a whole lot more work than a quotient rule would be. All right, another question off the review that you want to take a look at?
Number 3.
Okay, find the tangent line to this function at x equals 1. So to find a tangent line, find equation of a line, I need 2 pieces of information. I need a slope and I need a point. Okay, To get the slope, we plug into the derivative, right? So the slope is f prime of 1. So first I find what f prime of x is. So we get differentiating this 3x squared minus 5 plus 0. So then the slope is the derivative when I plug in 1. So 3 times 1 squared minus 5, which gives me negative 2. Okay, so now I have the slope. Now I need a point. I have an x value. I get a y value by plugging into the function. So y is f of 1. So this is 1 cubed minus 5 times 1 plus 2, which is 1 minus 5 plus 2, which is negative. It's also negative 2. Okay. So now I have a point, 1, negative 2, and I have a slope, negative 2. So then I'm going to use the point slope form of the line. Y minus y1 equals m times x minus x1. Okay, so y minus negative 2 equals negative 2, x minus 1. Distribute my negative 2. I have minus a negative. Right, that happened twice. And now I subtract 2 from both sides. So I get y equals negative 2x. Okay. Any questions on that one? I feel like I went through that one too fast. I'll slow down for the next one. Another review question.
Five.
Okay, on problem 5, what makes this one challenging, I think, is that when I look at this, I see 3 multiplied pieces. But our product rule only works for 2. So what I'm going to do is I'm going to divide this up, or break this up, into 2 multiplied pieces. That's how my product rule works.
I have a question just on that.
Yeah.
So, like, how do you know which two pieces like to choose? Because like when I had originally done it, I'd just taken 4x to the 6 times like the second bit.
Okay, then do that.
And would that be fine too?
Absolutely.
Okay, because you're then gonna still basically do the same steps.
You're going to do the same steps, and your unsimplified answer will look different if you do it differently. Your simplified answer will look exactly the same. So, you know, it doesn't matter which way you break it up.
Okay, thanks.
Okay. So we're going to take the derivative of 4x to the 6th times this other piece left alone plus 4x to the 6th times the derivative of this piece e to the 3x times sine of 2x. Okay. And then the derivative of 4x to the 6th, I use the power rule, so the 4 comes down. So we get 24x to the 5th times this stuff. And you can write the parentheses, but they're not really necessary because it's all just multiplication here. Okay, and then plus 4x to the 6th times this derivative. Now this derivative is another product rule. Okay, so I have the derivative of e to the 3x times sine of 2x left alone plus e to the 3x left alone times the derivative of sine of 2x. Okay, so now when I write out my next line, the stuff here in brown is all done. Okay, so now when I differentiate e to the 3x, 3x is a function inside this exponential function, so I'm using the chain rule. The derivative of e to the x is e to the x. When I differentiate a function, I plug in that inside function. So I'm going to have e to the 3x times the derivative of the inside function, which is 3. Same thing over here, sine of 2x. 2x is an inside function. So my outside function is sine. When I differentiate, I get cosine of the inside function times the derivative of the inside function. Okay, now this says don't simplify, so we could just call it here, and that's fine. Okay, and again, if you broke this up differently, if you wrote 4x to the 6th times e to the 3x is your first piece and sine of 2x is your second, your answer is going to look different from this, but it will also be correct. The simplified answers would be the same. Okay, so don't worry about that for the test, right? If it looks different but it's correct, then it'll get marked correct. Okay, another review question.
Number 7.
So number 7, when I look at this, I've got a bunch of stuff inside the cotangent function. So I'm going to start with a chain rule. So I have to remember what the derivative of cotangent of x is. Since it's a cofunction, I know I get a negative on it. And if I remember that the derivative of tangent x is secant squared x, then cotangent sort of mirrors that, except with cotangents and cosecants. So I get cosecant squared x. Okay, when I use the chain rule says take the derivative of the outside, right? So I have cotangent of stuff. My derivative formula is negative cosecant squared x. But the chain rule says don't plug in x, plug in the inside function. So I get negative cosecant squared of this inside function. And then times the derivative of that inside function. Okay. Now, to work out the derivative of this inside function, this is a quotient rule. Okay. So my next line of equality here, I have the negative cosecant squared of cosecant of 5x over x to the 4th minus 2x plus 3 times, and then I'm going to set up my quotient rule. Quotient rule is the derivative of the top times the bottom left alone minus the top left alone times the derivative of the bottom all over the bottom squared. Okay, so now I have to work out these two remaining derivatives here. Oops. So now I'm going to work out these two derivatives. Since I don't have to simplify my answer, I'm leaving everything else that I've already finished. I'm just going to leave it alone. Okay, so the derivative of cosecant of 5x. Well, I had to remember the derivative formula for cotangent. Now I need to know the derivative formula for cosecant. It's a cofunction, so I know it's negative. And again, if I remember back, I don't know if this helps you, maybe if you remember the derivative of secant is secant x times tangent x. For cosecant, you get kind of the same thing, except with cosecants and cotangents, right? So we get negative cosecant x cotangent x. But I don't have an x that I'm as my inside function. I have a 5x. So I'm using the chain rule here. The chain rule says do your derivative formula, but don't plug in x, plug in the inside function. So instead of plugging in an x, I'm going to plug in a 5x. So I have negative cosecant of 5x cotangent of 5x times the derivative of the inside function. The derivative of 5x is 5. Okay, and then over here, the derivative of x to the fourth minus 2x plus 3, that's nice and easy, right? Power rule, right? And the derivative of 3 is 0. Okay. Little 4's getting messed up. Okay. Does that make sense?
Yep.
Okay, and again, please don't start simplifying this. That's not, doesn't seem like a good idea. It just turns into a big mess. Okay, any other questions off the review?
Number 9.
Before I start differentiating number 9, what I'm going to do is rewrite this square root as a 1/2 power, right? So I have arctangent of x squared to the 1/2. And arctangent is the same as tangent inverse, right? So tangent inverse x is the same as arctangent x. And I know that the derivative formula, or maybe I can go look up the derivative formula, right? We used that earlier from 3.7. It's 1 over 1 plus x squared. Now, just to make a note on this, I just said go look this up. On the exam, I'll give you this derivative formula for arctangent, so you don't have to memorize it. Okay, what you do need to be able to do, though, is say, well, it's not arctangent of x, I have an arctangent of x squared. I need to know how to use this derivative formula when I have a chain rule problem. And in this case, I've got like a double chain rule. Okay, so let's go through this. When I go to differentiate, my outermost function is stuff to the 1/2 power. So I get 1/2 inside stuff to the -1/2. Chain rule says the inside function stays the same. And then you multiply by the derivative of the inside function. Okay, so that's the first chain rule step. Now, the derivative of the inside function is arctangent of x squared. That is its own chain rule problem. Okay, so I'm going to use this derivative formula, 1 over 1 plus x squared. But I'm not taking the derivative of arctangent of x. I'm taking the derivative of arctangent of x squared. So I don't plug in x, I plug in x squared. So I have 1 over 1 plus x squared times the derivative of x squared. Okay, and the derivative of x squared is just 2x. All right, so I'm going to just write this as 2x over 1 plus x to the 4th. Does that make sense? Hopefully.
Can you just explain one more time how you got it to be 2x on the top?
Yeah, so I'm using the chain rule. My x squared is the inside function. Okay. The chain rule says do the derivative formula, but instead of plugging in x, I plug in the inside function. Right? The inside function is x squared, and then multiply by the derivative of the inside function. Okay.
Got it.
Okay. So yeah, instead of writing times 2x, I just wrote the 2x in the numerator. Okay, any other questions off the review?
Number 10.
Yep. So number 10, you could just start differentiating it as it is, but what I would do is say, well, if I've got a log in here already, I'm going to use any log rules that I possibly can before I take a derivative, just to make things easier. So I would write this as ln of 1 plus e to the x plus e to the 2x minus ln of 1 minus e to the 3x. And that way, when I go to differentiate, I don't have to do a product rule at any point. I'm sorry, a quotient rule at any point. Okay, so now let's go ahead and take a derivative. All right. So if I have natural log of stuff, I have to use a chain rule where this inside stuff here, that's my inside function. And I know that when you take the derivative of ln of x, you get 1 over x. So when I use the chain rule and I take the derivative of ln of some function of x, I get 1 over that function times the derivative of the inside function. Right? That's what the chain rule says. So I'm going to get 1 over this inside function times the derivative of the inside function. So we get 1 over 1 plus e to the x plus e to the 2x times the derivative of the inside. Well, instead of writing it as 1 over and then times derivative of the inside, what we typically do is we just write times the derivative of the inside as the numerator. It's just keeping things a little bit more compact. Okay, same thing over here. My inside function is 1 minus e to the 3x. So then we have times the derivative of 1 minus e to the 3x. Okay, so now let's go ahead and do our derivatives. The derivative of 1 is 0. The derivative of e to the x is e to the x. The derivative of e to the 2x, I'm doing the chain rule. Since the derivative of e to the x is e to the x, when I have a function, right, I'll just get e to the 2x times the derivative of the inside stuff. Okay, same thing over here. The derivative of 1 is 0. So I have minus, and the derivative of e to the 3x is e to the 3x times the derivative of the inside stuff, so times the 3. So you don't have to simplify. If you did, I guess the way that I would usually write this would be plus 2e to the 2x. And here I have minus a negative, so it's going to be plus 3e to the 3x. Okay. So unsimplified, mostly simplified. Combining these fractions together would just be a mess. That's not worthwhile, so we're definitely not going to do that. All right, does that make sense?
Yeah.
All right. Okay, well, nobody asked yet, but I'm just going to go ahead and do problems 11 and 12 because I think that the last couple problems are usually the most challenging, right? And these two are no exception. So for this one, I want to find the derivative of this function. At least, let's say, somewhere back here, find the derivative of all these. Yeah, differentiate the function. Okay. Okay, so I need to find the derivative of this thing, but this is terribly complicated. So I'm going to go ahead and use logarithms to help me break it up. So I'm going to start by taking the natural log of both sides. And then on the right-hand side, I'm going to use my properties of logs to break this one complicated log up into a lot of simpler pieces. Okay, so in my first step, what I'm going to do is all of the pieces in the numerator are going to be added logs. And the pieces in the denominator, because I'm dividing by those, they're going to be subtracted logs. So I'm going to have ln of x cubed plus ln of x plus 1 to the 5th plus ln of x plus 2 to the 8th minus ln of x plus 3 to the 9th minus ln of x plus 4 to the 10th. And then I can use my other property of logs that says if you have ln of something to a power, you can bring that power down out front. Okay, so ln of y is going to be 3 ln x plus 5 ln x plus 1 plus 8 ln x plus 2 minus 9 ln x plus 3 minus 10 ln x plus 4. Okay, now we differentiate both sides. Okay, the derivative of ln of y is 1 over y times the derivative of y, so times dy dx. On the right, I have 3. The derivative of ln of x is 1 over x. Nice and simple. For all the rest of these, I'm using a chain rule. So we have 1 over the inside function times the derivative of the inside function, but the derivative of x plus 1 is just 1. Okay, 1 over the inside function times the derivative of the inside function. 1 over the inside function times the derivative of the inside function. Okay, 1 over the inside function times the derivative of the inside function. Now these are all very simple inside functions. All of their derivatives were just 1, but that may not be the case for every problem. Okay, so you want to just keep in mind that it's not if it's anything more complicated than x, you're using the chain rule. Okay, so I multiply both sides by y. So I'm just going to write this a little bit more cleanly as I go. So 3 over x plus 5 over x plus 1 plus 8 over x plus 2 minus 9 over x plus 3 minus 10 over x plus 4. And then for our last step, we replace the y with the formula that we have for y. So dy dx is x cubed, x plus 1 to the 5th, x plus 2 to the 8th, over x plus 3 to the 9th, x plus 4 to the 10th, times this stuff in parentheses, 3 over x, plus 5 over x plus 1, plus 8 over x plus 2, minus 9 over x plus 3, minus 10 over x plus 4. Okay. Any questions on that one? Okay, so let's look at questions 12 and 13. 12 and 13 both involve implicit differentiation, and again, this is, logarithmic differentiation and implicit differentiation, I definitely think are the hardest topics in chapter 3. So let's go ahead and look at taking the derivative of this thing. I want to find the equation of the tangent line. So what I want to do is take the derivative and then plug in to find the slope of the tangent line. Before I take the derivative, I'm going to rewrite this as x times y to the 1/2 power, right? So I like to rewrite my square roots as 1/2 exponents. Okay, so now I'm going to go ahead and differentiate both sides. The derivative of x squared is 2x. Here I'm using the chain rule where x times y is my inside function. So I have 1/2 inside function to the -1/2 times the derivative of my inside function. Okay, when I differentiate 2y squared, y is my inside function, stuff squared is the outside, right? So the 2 comes down, lower the power by 1, so it's a 1, times the derivative of the inside function, so times that dy dx. Okay, so when we're differentiating with respect to x, anytime we differentiate something that has y's in it, we should get a dy dx that comes out. All right, the next step, I'm differentiating x times y. This is a product rule. Okay, so this other stuff I'm just going to write out. So in parentheses, I'm going to do the product rule. So we have the derivative of the first times the second plus the first times the derivative of the second. Derivative of y we write as just dy dx. Okay, now what we do next depends on the problem. We could solve for dy dx. That's fine. In order to break these two up, I need to distribute this thing to the y and to the x times dy dx so that I have them as separate terms so that I can subtract stuff that does not have dy dx on one side, everything with dy dx on the other, factor, divide. Okay. In this problem, though, I don't need a formula for dy dx. What I need is a slope of the tangent line. And the slope of the tangent line is just dy dx when I've plugged in x is 1 and y is 1. So what I'm going to do is, at this equation, I'm going to plug in x is 1 and y is 1, and then my dy dx is going to be the slope of the tangent line. So 2 times 1 is 1/2. 1 times 1 is the negative half, times parentheses 1 times 1 plus 1 times m equals 4 times 1 times m. And now I can solve for the slope m, but I don't have all of these extra variables, and I think that makes the algebra a lot easier. Okay, 1 times 1 is 1. The negative half power is still 1. So I have 1/2 here, 1 plus m. So I'll distribute this half. I still have, whether I want to solve for dy dx or solve for m, I have to distribute to get rid of that parenthesis. So I get 1/2 plus 1/2 m equals 4m. Okay, subtract a half m from both sides. And I'm going to add these two fractions together. So think of this as 2 over 1. To get a common denominator, it's going to be 4/2 plus 1/2 is 5/2. 4m is 8/2 m minus 1/2 m gives me 7/2 m. Okay. And then just multiply both sides by 2/7. Okay. So then I get 5/7 equals m. All right. To get the equation of the line, y minus y1 equals m times x minus x1. So y minus 1 equals 5/7, x minus 1. Y minus 1 equals 5/7 x minus 5/7, and then add 1 to both sides. So y is 5/7 x. 1 is the same as 7/7. Negative 5/7 plus 7/7 is positive 2/7. So there's the equation of the tangent line at the point 1, 1. All right, any questions on that one? It's a tricky derivative with that half power. Okay, I think this is the last one on the review. Find the coordinates of the point in the first quadrant at which the tangent line to this, I don't want to call it a function, but this implicit function is horizontal. Okay, so a tangent line is horizontal. That means that the slope of the tangent line is 1. I'm sorry, is 0. So what I want to do is I want to solve for where the derivative dy dx is equal to 0. Okay, so what we're going to do is we're going to compute dy dx, and then we're going to set it equal to 0 and solve. All right. So let's go ahead and differentiate this thing. Okay, so the derivative of x cubed is 3x squared. To take the derivative of minus xy, I'm going to think of negative x as a function, y as a function, and use the product rule. Okay, so I have the derivative of the first, so negative 1 times y left alone, plus the negative x left alone, times the derivative of y, which is dy dx. Okay, when I differentiate y cubed, we're using the chain rule. Y is the inside function, so we get 3y squared times dy dx, and the derivative of 0 is 0. Okay, in this case, I do want to solve for dy dx, so I'm going to subtract 3x squared from both sides, and then I'm going to add y to both sides. Okay, so now I have negative x dy dx plus 3y squared dy dx equals negative 3x squared plus y. Okay, so now everything on the left-hand side has dy dx in it. I'm going to factor dy dx out. I have negative x plus 3y squared left over. And then I divide to get dy dx by itself. Okay, so that's the derivative dy dx. We just said that if I want to find out where I have a horizontal tangent line, that's where the slope is 0, so that's going to be where the derivative is equal to 0. I now have a formula for the derivative, so I'm going to set that equal to 0. A fraction is going to be equal to 0 when the numerator is 0, so what I'm really doing is I'm solving negative 3x squared plus y equals 0. But I only have one equation here. That's not enough to actually find out what's going on. I can't solve for both x and y with just one equation. So I can write y equals 3x squared, but I'm sort of stuck here for the moment. But I know that the points are going to be on this graph. So I also have the equation x cubed minus xy plus y cubed equals 0. So I really do have two equations. Okay, so I'm going to solve using substitution, and this first equation gives me that y is 3x squared, so I can replace my y's with the 3x squared. Okay, so now I have an equation with just one unknown. Let's see how that goes. So I have x cubed minus 3x cubed plus, when I cube this out, 3 cubed is 27. X squared cubed, when you take a power to a power, you multiply the powers. Okay, so I have 27x to the 6th minus 2x cubed equals 0. And this one can be, I have an x to the 6th power. There's a couple different ways, I think, to solve this. I think the easiest thing to do is just to factor whatever factors out, right? I can take an x cubed out of the whole thing. Okay, and when I have factored stuff equal to 0, I can set each piece equal to 0 separately. Okay, so I get x cubed equals 0, or x equals 0. Okay. We'll come back to our individual answers in a minute. Let's go ahead and solve the other one. So now I have 27x cubed minus 2 equals 0. So 27x cubed equals 2. X cubed equals 2 27ths. So x is the cubed root of 2 over 27, which is cube root of 2 over 3. Okay, it says find the coordinates of the point in the first quadrant. If my x value is 0, I'm not in the first quadrant, I'm on that axis. Okay, so this guy is not in the first quadrant. For this next one, I have an x value. To find a y value, I can just use this other equation I have. Y is 3 times my x value squared, okay, which is 3 times 2 to the 2/3 power over 9. The 3 and the 9 cancel a little bit, and I get 2 to the 2/3 over 3. Now I have an xy coordinate, and that's all I'm looking for. It says find the coordinates of the point. Okay, so the coordinates of this point are, my x value is, you could write this as cube root of 2, or I could write it as 2 to the 1/3 over 3, and then 2 to the 2/3 over 3. And I think that's probably the easiest way to write the coordinates of that point. Okay, that one was definitely complicated. Any questions on that one? Okay, well, if you come up with any more questions, you can feel free to send me an email, and we can go, I can respond. If it's complicated, we can set up a meeting. But otherwise, I think we'll call that it. I'll let you finish up homework and study away. Remember that tomorrow morning is our exam too.
I thought of one question.
Yep.
What did you say will be provided to us? Like you were saying, like the inverse
Yeah,
formulas.
so
What is that the only thing, or?
what I'm going to do is, I think I'll send out, I'll make a Blackboard announcement, and I'll send out exactly what's going to be provided so that you can see that in print.
Okay, perfect.
Yeah. Any other questions? Okay. Then I think we'll call this it for right now.
Right, thank you.
Thank you.